All right. Welcome to, I guess, the last.
There is one more there.
One more. Okay. The second last theory lunch of the term. We are very happy to have Tim Hsieh from MIT. Tim was a student at Carnegie Mellon, and now he's a CLE Moore instructor in the math department at MIT. He has amazing works to his credit. He has done foundational work in coding theory, analysis of algorithms on average case inputs. And he has this amazing sequence of works in pseudo-random constructions or explicit constructions, one of which won him the Best Paper Award at Fox Conference last year. And so that's basically the work he's going to tell us about today, but we were able to get him to actually talk about the entire history of this work, which is based on two earlier papers of his, which develop some of these beautiful ideas. And so, yeah, Tim, take it away and explain to us how this breakthrough came out.
All right, thank you so much for the introduction. Yeah, today this talk will be based on three papers. These are all papers about explicit constructions of vertex expanders, and with some amazing collaborators, and two of them are actually in the audience. So the first one is about constructing unique neighbor expanders, and the second one is about vertex expander beating some barrier, and the final one just lossless vertex expander. So I'll explain what all these mean. And today I'll talk about this general framework that we call the tripartite line product that underlies all three constructions. I'll talk about that. I'll actually spend most of my time talking about the first paper, which I believe the analysis I can fit in a 1 hour talk. And then I'll say briefly how high dimensional expansion helps us get improve this paper and get these two papers. So that's the rough outline of this talk. Okay, let me start with an expander. So an expander is a graph that is both well-connected and sparse. So for example, we know that a clique is very well-connected, but it's still dense. It has degree n. So we would like sparse graphs that is also well-connected. And here sparse, we want it to be constant degree, ideally. And there are three main notions of expansion: vertex, spectral, and edge expansion. These bottom two, spectral and edge, we know we understand them pretty well. We have many explicit constructions of these spectral expanders. And we know that these two are roughly equivalent by the Cheeger's inequality. This vertex expansion will be the focus of the talk today. It's, I guess, a little bit less well understood. And I also talk a bit about the connection between vertex and spectral expansion. Okay. So let me first define what vertex expanders are. At a high level, we want that every small subset to have many different neighbors. So here's an example. Let's look at this set S, and this is colored green. The red vertices are its neighbors. So intuitively, you just want S to have many different neighbors. More formally, we say that a graph is a regular graph is a gamma vertex expander if the number of neighbors of S, n of this, is at least gamma times d times S. Here, gamma is some parameter that's at most 1. So we know that ds is the number of edges going out of S. So it cannot be more than, gamma cannot be more than 1. And we want this to hold for every set of size at most eta n. And here, eta is some constant that depends only on d, but not on n. So this basically means that we want all linear sized subsets to have many different neighbors. Ideally, we want gamma to be as close to 1 as possible. And if we're able to get 1 minus epsilon, potentially by increasing d, depending on epsilon, then we call this graph a lossless expander. Okay. Let me first quickly mention that there are many different applications of vertex expanders. I'll quickly say one simple one, LTPC codes. So if we use a bipartite vertex expander as the parity check matrix, and we put code words here and then parity checks here, then it's a very simple calculation that gives that this code must have linear distance. And the intuition is just that if you have corruptions that are not, there are too many corruptions, then the parity checks are going to catch it. And by expansion, if any linear size subset has good expansion, then we will be able to catch linear size corruptions, and this kind of means that the code has linear distance. And so this is a very simple application of vertex expanders, and there are actually many, many more in TCS, which I won't go into detail here. Okay, so that's a quick application of vertex expanders. Now I'll tell you a slightly different notion of expansion called unique neighbor expansion. Here we define unique neighbor to be vertex, a neighbor of S that has exactly one edge going back to S. Let's look at an example. This is a set S here. It has many different neighbors. So if you look closely, you can see that every vertex or every neighbor has two edges going back to S. So this set actually has 0 unique neighbors. It turns out that many applications that I listed in the previous slide, including the application for LDPC codes, the correct notion is actually unique neighbor expansion. You need unique neighbor expansion to catch these errors in the LDPC code. Okay, there's a clear connection between vertex and unique neighbor expansion. Here's the following. If you have 1 minus epsilon vertex expansion, then it implies 1 minus 2 epsilon unique neighbor expansion. This is a simple just counting like degrees. So if this is close to 1, then these two are roughly the same. But more generally, if you have gamma vertex expansion, then you get 2 gamma minus 1 unique neighbor. Notice here that gamma being half is actually a barrier here. If gamma is larger than half, then you get some non-zero constant here. But if gamma is below half, you don't get anything. And this gamma equals half barrier will show up later in the talk. Okay, yes. So now let me tell you a bit about what we know so far. So let's think of random graphs. Random graphs we know are 1 minus epsilon vertex expanders with high probability. They're very good lossless expanders. So that's great, but there are several drawbacks of using a random graph. First of all, it only holds with high probability. So it's not guaranteed that every time we sample, we get a lossless expander. And in fact, there's a recent paper showing that some hardness evidence saying that it's likely no efficient certification algorithm to verify that the graph you sampled has good vertex expansion. Even though it satisfies a high probability, not always guaranteed, and you cannot even verify. There's another reason why random graphs are not so ideal. In certain applications, we actually need the graph to have structure. For example, there's an application of lossless expanders to construct quantum LDPC code. And in this application, you need the graph to have certain free group action. I will not go into detail what this means, but this is the structure that random graphs don't have. So this leads to the question of explicit constructions. Yes, explicit means that we want to have a deterministic algorithm that generates the graph in polynomial time. And in our paper, we'll see that our construction all have this group action property. So, okay, any questions so far? Okay, and I'll tell you a bit about some previous constructions. Today, I'll focus on the bipartite case. So every graph today is about the bipartite version. We actually know very good one-sided lossless expanders from 2002. This is a famous paper. This means that you have a bipartite graph, and subsets on one side have lossless expansion to the other side, but there's no guarantee on subsets of the other side. And there have been some recent simplified construction in recent years. There's another work on unbalanced two-sided lossless expanders. Here, unbalanced means that the two sides of the bipartite graph is polynomially different. And the techniques as well as applications are very, very different from our setting. And also here, even the smaller degree side, the larger side, which has smaller degree, they need polylog degree. So it's actually still an open question whether you can get imbalanced, polynomial imbalance, but constant degree on the smaller side. Sorry, larger side, smaller degree side. Today, our goal is two-sided, constant degree, and constant imbalance. Okay. So before I tell you the construction, let me switch gears and talk about special expansion, because we understand this pretty well. And I also talk about the connection between these two. Okay, what are special expansions? So we take the adjacency matrix of a graph, and we look at this eigenvalues. We know that the first eigenvalue will always be the degree d, assuming it's a d regular. So we say that this graph is a special expander if the second eigenvalue is much smaller than d. And this already implies many interesting properties: high conductance, low subgrid densities, and rapid mixing, etc. So for a lot of different applications, spectral expanders is the right notion of expansion to look at. And for deregular graphs, we know that the optimal spectral expanders are these Ramanujan graphs. These are graphs where the second eigenvalue is at most 2 root d minus 1. So this is the first time you see this quantity, a bit mysterious, but it's actually the special radius of this infinite deregular tree. We also know this optimal because we know that every deregular graph must have lambda to at least this minus this over 1. Okay, and again, random graphs also are very good special expanders. They're almost Ramanujan with high probability. There's actually a very recent paper showing that random graphs are exactly Ramanujan without the almost, with some probability 69 or something, 69%. Okay. As for explicit constructions, we actually know many different constructions of Ramanujan graphs. We know algebraic ones. These are famous constructions in the 80s, Marconi's and also LPS graphs. We also know complementary constructions by some two-lifts and derandomization. Actually, Sidhanth and Pedro sitting in the audience here. The bottom line is we know many different ways of constructing good special expansions. So the question is, does special expansion imply vertex or unique neighbor expansion? Okay, the quick answer is yes. Kahale showed that Ramanujan graphs have half vertex expansion. Turns out this is tight. There are Ramanujan graphs with vertex expansion half, but 0 unique neighbor expansion. So remember, half is the threshold where you don't get any unique neighbor expansion below this. So there are Ramanujan graphs where this kind of structure exists, where there's a subset S which has many neighbors, but no unique neighbors. This structure can exist in Ramanujan graphs.
Okay.
Yeah.
What Ramanujan graphs actually have this tightness property? Do we know?
Yeah, so I think Morgenstern's
Morgenstern.
graphs have it. Yeah. And Kahale actually showed some that I think you can embed this small set in here into a Ramanujan graph, so that is still almost Ramanujan. But yeah, this newer paper by Kemper and Kaufman, they showed Morgenstern's graph actually have this. Okay. So now talk about our results. This is a special barrier path. In the first paper, we get gamma unique neighbor expander. That's the first two-sided gamma unique neighbor expanders with some small universal constant gamma. In the second paper, we're able to break this special barrier and get 0.6. And then finally, in the third one, we get lossless expanding, 1 minus epsilon vertex expanding. Okay. So here's the main theorem statement. For every constant epsilon and also any constant imbalance, beta, we can construct explicit two-sided 1 minus epsilon vertex expanders. So here's a picture. We want that every, this is a CD regular graph, and the ratio between C and D is beta. We want that every subset S on the left has at least 1 minus epsilon C times S neighbors on the right. And then every set T has at least 1 minus epsilon times D times T neighbors on the left. Okay, that's it. That's our main result. And in fact, all these papers use the framework that we call the tripartite line product. And this is the product that I'll talk about next. Let me pause a bit for questions. Okay. So the next part is about tripartite line product. There are two ingredients in this product. First is a large infinite family of tripartite graphs. We call this a base graph. And the second ingredient is the gadget graph, which is a constant size random graph. Here we say random, even though we want a deterministic construction. This is because we have a constant size. It's a constant size where we can brute force search over all the graphs and find the best one. Usually the random graphs are the best ones. And let me first tell you the high-level idea of what's happening. Because random graphs are lossless expanders, so we can find a gadget graph that is a lossless expander. But this is only a constant size. And then we want to choose these base graphs appropriately, so that we can amplify these expansion properties to the large graph. And this is very similar to, or this is what has been has appeared in a lot of different applications in TCS, this local to global phenomenon. We're lifting a small random looking object to a large object. This is a high level description. So let me now tell you about the construction. So we have start with two vertex sets. So even though we call this a tripartite graph, it's actually two bipartite graphs. The left, middle, and right. We put a bipartite graph between L and M. This is, we have K left degree, D right degree. And then we put another bipartite graph in between middle and right. Again, this is capital D degree and K degree on the right. That's it. That's our base graph. The base graph is a tripartite graph. It actually consists of two bipartite graphs. And here for simplicity, I'm assuming that K, D, DK are the same. But if you want some constant imbalance, you can choose K1, D1, D2, and K2. These are some knobs you can choose. Okay, the gadget graph will be a bipartite graph on capital D and capital D vertices. And it's very important that the number of vertices here match the degree here. Okay, and we'll see in a second why. Now let's look at the construction. We focus on one vertex in the middle. It has D neighbors on the left and D neighbors on the right. Now just put a copy of the gadget graph here. We connect these D left-right neighbors according to H. And we do the same thing for the next vertex. We look at its D neighbors on the left and right, and then connect them based on H. And we do that for every vertex in the middle. In the end, we will remove the middle, and we get the bipartite graph between left and right.
And parallel edges are okay?
Parallel edges are okay. And in fact, we will show that because the lossless is expanding, so that won't happen too much. Yeah. Okay, so that's it. And we can quickly see that the final degree is K times DH, because each vertex on the left has K neighbors. And each neighbor there's going to be a gadget graph there. And the gadget graph has degree DH. So the total degree is KDH. Okay. Now, let me talk about the choice of base graphs. So the gadget graph is random, so there's really no innovation there. You just choose a random graph. The base graph is the important part. In the first paper, we choose these two bipartite graphs to be Ramanujan graph. This is perhaps maybe the first thing to try once we define this product. well, we want these two bipartite graphs to be expanding, and Ramanujan graphs are natural constructions to try. So this is a bipartite graph. There's a natural generalization of Ramanujan graphs to the bipartite version. This is the graphs where the second eigenvalue is almost root k minus 1 plus root d minus 1. And again, we know many constructions of these Ramanujan bipartite graphs. This gives us two-sided gamma unique neighbor expansion with some small gamma. In the next paper, we realized that high-dimensional expansion can help. We use the phase vertex incident class graphs of these Ramanujan symplectic complex. This is a mouthful, but it's just there's some high-dimensional structure in these bipartite graphs. And using this, we're able to get 0.6 unique neighbor expansions. Particularly, this breaks the spectral barrier of half. Okay, in the third paper, instead of using these simplicial complexes, we use something called the cubical complex. Yes,
If it's 0.6 unique neighbor, you mean like 0.6 vertex expansion and 0.1?
Yeah, so actually I said 0.6 vertex expander previously, but we actually get 0.6 unique neighbors too.
Oh.
Yeah.
So you don't have to use this 2 gamma 1 as well.
Yeah. So in our paper, we directly analyze unique neighbors. So we do get 0.6 unique neighbors, not just it's 2 gamma minus 1. Yeah, thanks. Okay, yeah, in the third paper, we were able to use this cubical complexes and then get, get lossless vertex expanders. So the bipartite graph is going to look like this, where we have cubes on the left and right, and then vertices in the middle. Okay, and before I move on, I want to show you an AI-generated cube picture studying the cubical complex. Yeah, okay, but any questions?
Which one is you?
I'm the side Okay.
Is there intuition why this construction will provide a lot of neighbors?
Oh yeah, because that's what you mean why high-dimensional expansion helps?
Well, like even with the first paper that you just used from looking around
Yes.
the middle, like why do you expect a lot of neighbors?
Yeah. So even here, right? I guess we kind of that's what I will talk about next. But intuitively, you can see that if you have any set here, it'll have a lot of neighbors in the middle. That's good expansion to the middle. And each vertex in the middle, when you zoom into the gadget there, it also gives you a lot of neighbors.
Yeah, but it doesn't unique.
So we need to argue about that. Yes. That's going to be the next part of the talk. Yeah, so the next part of the talk will be about our analysis.
Actually, can you pause one more question?
Yeah.
Do you need to, even for the first result, do you need to instantiate with Ramanujan graphs, or like could weaker expanders suffice for getting unique neighbor expansion?
Oh, wait, what do you mean by weaker? How weak?
Like, do you really need 2 root d minus 1, or like some big O of root d minus 1 root d suffices, or
O root d suffices.
O of root d?
Okay. Yeah, okay, so now I'll talk about the analysis. And actually, all three papers, their analysis kind of follow the same blueprint. There are 2 parts of the analysis that we need to do. So let me explain that. Okay, here's the outline. We want to say that for any S on the left, it has many neighbors on the right. That's what we want. So let's first look at the expansion to the middle. Let's let U be the neighbors of S in the middle. And I want to tell you some best case scenarios that we would like. And show you that the best case scenarios immediately give us lossless expansion. So the first best case scenario is that when S is losslessly expanded, this means that U is K, which is the degree, times S size. And that's great for us. This means, in particular, that any vertex in U has one left neighbor in S. So this is a picture. this vertex has D neighbors, but only one intersects S. So this is good for us. Why? Because now when we zoom into this gadget, we're placing this gadget here. This intersection, there's only one vertex here. And by the expansion, or it doesn't even need expansion, there's only one vertex. So within the gadget, we'll have DH neighbors. This corresponds to DH neighbors here. So this vertex here contributes DH neighbors in the final product. Okay, good. We actually don't need it to be just one, it can be a few. Instead of one, we have maybe a few left neighbors intersecting S. And that's just some threshold tau. So the intersection between S and the left neighbors of U is at most tau. If tau is not too big, this is still okay because we zoom into the gadget, this set has at most tau vertices. And because the gadget is lossless is expanding, we also have many neighbors on the right. Okay, so and because this is lossless expanding, we will get DH times the intersection size different neighbors on the right. Yes.
So how do we put the gadget in every graph? Do we in any artificial way works?
Great question. For the Ramanujan graph construction, you can put it in any way, I think. But for the two other papers, it's very important to put it in a systematic way. So I won't go into the detail. Yeah, I was planning to sweep this under the rug for this talk, but it is important that in the second and third paper, these graphs are tiled correctly. So in the bipartite graph, we'll have gonna be some like you'll have labels for each edge. And we need to tile them according to the labels. Thanks for the questions. It's actually an important detail.
And also, so you only explained what happens to a single little u in the middle.
Yes.
In principle, there could be conflicts between. So you could kill the whole expansion.
Yeah. So that's best case scenario number 2.
Okay.
Yes. Good. Okay. So hopefully best case scenario number 1 is clear. Yeah. Best case scenario number 2. There are no collisions between different gadgets. Because this vertex contributes some neighbors. The second vertex in U also contributes some different neighbors. The best case scenario is when they don't collide. Then we're happy. And now I'm going to finish the proof using these best case scenarios. Combining them, we get that the neighbors of S is going to be the sum over each U in the neighbors of S. This set is capital U. DH times intersection size. And this DH time, we get this DH factor because the gadget is lossless expanding. And we're able to safely sum them over because of best case scenario number 2, which is there are no collisions. But if you sum over this quantity, this is sum over the intersection size. This is precisely the number of edges between S and its neighbors. This is precisely K times S. So we get K DH times S. Remember, our degree of the graph is KDH. So that's it. We get that the number of neighbors is roughly the degree of the final graph times the size of the set. Yes?
This analysis only works when you only have 1, 2 cases,
Yes, yes.
and you still have other cases to handle.
This is 1 and 2 are basically the 2 parts of the proof that we need to analyze. We need to show that for most overall, on average, they behave like this. Yeah. But actually, I think in all 3 papers, our proof is split into 2 parts, 1 and 2. Yeah, so great question. This is the next thing I'll talk about is how do we avoid these collisions? And there are 2 types of collisions. The number 1 is collisions within the same gadget, and number 2 is between different gadgets. Okay, and it turns out that for both of these cases, it comes down to rolling out certain dense subgraphs in the bipartite graph. Okay, so I'll now dive into the details of this. But at a high level, it's about rolling out dense subgraphs in these two bipartite graphs. So you can imagine why choosing a good expander for these two helps. Okay, let's see. So let's first look at the first type of collisions. So this in the bad case here, we have that this intersection size is too large. But just like the previous picture, but now the intersection size is too large. What happened here? We look at this gadget, this set is too large. And there's a threshold of capital D divided by the gadget degree. This is too large because we only have capital D vertices on the right. So this multiplied by DH will be larger than the number of vertices. And that's never going to happen. So we cannot, if the intersection size is larger than this, we cannot have lossless expansion. Meaning there's just no room to expand. Okay, how do we want to roll this out, basically? So let's call these vertices bad. U bad are the set of vertices in U, where the intersection is larger than this threshold. Okay, the goal here is to say that most of U is good. And to show that, we want to show that the number of edges from S to this bad set is very small. It's only an epsilon fraction of the total edges going all the way. Yeah, here's a picture. This corresponds to rolling out this dense subgraph within the bipartite graph. Here we have S bad, which is have epsilon k edges to the left, and then U bad has at least capital D over DH degree on the right. We want to say that this doesn't exist. Any questions? Okay, how do we roll this out? Well, we can use expansion. Okay, this is the same as what I said. We want to roll out this dense subgraph. And the idea is to use expansion of the graph. Okay. Now we're going to choose bipartite Ramanujan graphs. And using so first of all, these are optimal special expanders. So when we can use an expander missing lemma argument to get a special bound of this We need DH to be at most root KD. And first, let's maybe unpack a little bit. So we need DH to be small enough so that this is large enough, it's dense enough for us to be able to roll it out. And if we do the calculation, special bound calculation, this is what we get. Yeah. Okay, I did not plan to go into detail of how we got this down, but actually it's just the product of these two and take a square root basically. But it's a simple, it's like kind of straightforward calculation. Yeah. Okay, now let's look at the second type of collision. These are collisions between different gadgets. And the picture looks like this. Now these two vertices have a lot of different collisions. Okay, we're going to say there are a few of these, which means that if you look at the red edges here I'm going to color an edge red if there's a vertex U and a neighbor here. I'm going to color this edge red. Okay. And the red edges form a subgraph of the bipartite graph on the right. And we want these red edges to be average degree 1 plus epsilon on the right side. So if it's at degree 1, then we don't have any collisions. You want it to have average degree 1 plus epsilon. This corresponds to rolling out a different dense subgraph with different parameters. The left degree is at least DH, right degree is at least 1 plus epsilon. We can basically use the same spectral bound and get this. DH must be at least root KD. Okay, so let's summarize what we have so far. In order to avoid the first type of collisions, we need K to be at most root KD. And the second type is we need DH to be at least root KD. and we get a contradiction. So that's bad news. But actually, it turns out that we still get something. We will still get a gamma unique neighbor expansion for some small gamma. And the way we do this is the following. We're going to set number 2 to be satisfied. So number 1 is not satisfied, meaning that there will have gadgets where there are too many, the subset is too large on the left. So this won't give us lossless expansion. But because the gadget is random, even though this set is large, we still have some constant unique neighbor expansion. Yeah, so that's how we get a gamma unique neighbor expansion, even though gamma is very small, some very small universal constant. Any questions about this so far? And actually, this is basically the entire analysis of our first paper. It's basically just we identify which dense subgraph to roll out, and we just apply spectral bound twice. And with this one final lemma saying that, or even though the set is larger than this, we still get some constant fraction. Unique neighbors. Yeah. So it doesn't really matter because we assume the difference is constant, factor difference. So yeah, like D1, D2 can be constantly, it has a constant factor difference. That's okay. And yeah, I think I forgot to mention that the entire same analysis is symmetric. So we're automatic. If we're able to get expansion on the left, we also get expansion on the right. Yeah. Okay. Cool. So okay, it seems that we hit a barrier here. We tried pretty hard, but it seems that there's no way to beat this just by using spectral Ramanujan graphs. So next, I'll tell you how the high-dimensional structure helps. Okay, it turns out high-dimensional structure is going to help the type 2 collision. Okay, and let's see how that works. This is the picture to have in mind for type 2 collisions. Okay, and I'll tell you the high-level intuition here. So let's look at a two-step walk from M, R, and M. This is a graph on the middle vertex set, and the degree is KD, like the product of the left and right degrees. Now we look at the collision graph. So what is this? Again, we color these edges red if there's a vertex U and it contributes some neighbors, and we color these red. There's a collision here. Look at this vertex. There's a collision here that gets two different red edges. Well, in that case, there is a linked to path between these two vertices. Okay, so we draw a collision graph like this. We draw an edge between these two vertices if there is a linked to path here. It can't be it can be a multi-graph. It doesn't matter. The point is that this collision graph is a subgraph of the two-step walk graph from middle, right, and middle. Is that clear? So now we can use special expansion. And special expansion basically says that in a special graph, any small subset, the induced subgraph has average degree root degree. So this graph has degree KD. So the collision graph has average degree root KD. Okay. Any possible for questions?
Expand the level.
Yeah, this is expanding. Yes. So now we need to say that, oh, these are negligible. So we want that DH is much larger than this. So we get the same result. This is basically the same proof as like the previously where we show these two dense subgraphs. It's the same proof. There we're rolling out a dense subgraph in the bipartite graph. Here we want to roll out a dense subgraph in this MRM two-step walk graph. Okay. Now, let me tell you how high dimensional expansion helps to assembly. We again look at this MRM graph. Again, it will be degree KD. That doesn't change. The cool thing is, there's going to be, this graph is actually now a multi-graph with every edge having some multiplicity. Okay, so why is that? At high level, in a high dimensional expander, any two vertices, they're either not part of any face, or they don't have any common neighbors, or they have many common neighbors. So when they have many common neighbors, then there will be many two-step blocks that connect these two vertices. Okay. So in here we'll have a graph of degree d to the 1/2, but with multiplicity d to the 1/2. So these 1/2 and 1/2, this is the case for cubical complexes. If we use, in our second paper, we actually use some simplicial complex. For example, if we put triangles here, then these will be a different, it's like 1/3 and 2/3. Oh, sorry, 2/3 and 1/3. It doesn't really matter. The exponent, as long as it's smaller than 1, then we're happy. Okay, the key point is that we get some polynomial factor here. Now, this is something I would claim without proof in this talk. We can ignore this. And this is using the spreadness of the gadget. So the gadget is a random graph. Each subset has spread out neighbors. And this is something we use crucially in the paper. So essentially what it says that like these neighbors are not going to land in the common neighbors here. So this is a very quite high level, and I won't have time to go into detail. But this is what intuitively is happening. We can safely ignore this multiplicity.
So what does ignoring mean? Do you mean like this cannot happen?
Oh no. Ignoring means that we can essentially treat this graph as a lower degree graph. So we pretend that this graph is a lower degree graph, and we do the same spectral analysis. So that the collision graph will have root of this degree. But now it's way smaller. It will have a most d to the 1/4 average degree. And this is a key improvement of using high dimensional structure.
So let me just make sure I understood this correctly.
Mhm.
You're saying the degree is KD, but because of like this multiplicity, you really only know that there's KD to the 1/2
Distinct, yes.
two-step walk, and each one occurs basically with some square root d many copies of it. You're saying somehow you can just ignore these copies. You can just mod out by it or something,
Yeah.
and effectively the degree basically reduces. Is that?
Yeah. So I did not plan to talk about in detail, but basically this requires some analysis of the random gadget. So it's not, so we need some additional property, not just that it's losslessly expanding. We need that like you have some in this small random gadget, you have some certain fixed subset. Every set has neighbors that are kind of spread out. Yeah, this is like a high level property of what we need for the gadget. And you think of these buckets as each edge with multiplicity. So it's gonna be spread out. So effectively, of course we need to prove that, but effectively we can just kind of ignore it. Yeah. So you can see we get a much smaller requirement for DH. So that's great. So basically, for the type 2 collisions, we get a big improvement over Ramanujan graphs. What about type 1? Well, type 1, unfortunately, we can no longer use the spectral analysis. This is because if we use these phase vertex graphs, then they're not a Ramanujan graph. So yeah, they're not Ramanujan.
How do you have Gopi expansion?
No, I don't think so. Yeah. So we need to do something else for that. So this is actually going to be slightly worse than using Ramanujan graphs. The whole point is somehow magically this improvement beats this loss. Yes.
So the type 2 collision is about the GR, right?
Type 2 about GR, yes.
And type 1 is about GL.
Yes.
Why can't you just use Ramanujan graph for GL and analyze as before and then use the Newton mechanism for G2?
Yeah, that's a great question. So this will get one-sided expansion. You also need the others.
Oh,
And this is actually how you can also recover one-sided lossless expansion using our framework. Yeah, so actually, if you set the second bipartite graph to just stars, then there's no type 2 collisions in it. Then this also gets a construction of one-sided lossless expansion.
So it very clearly recovers the CDRW type.
Yes, yes. This is like our and this, what I just said is like the last section in our in the first paper. Yeah. You just use red bipartite graph to be stars. So type 2 is just completely gone. Yeah, okay. So for to handle the first type collisions, in this paper we use simplicial complexes. And this comes down to studying these triangle densities. Triangle density balance. What this roughly means that in this complex, if you take a subset of vertices, there are not too many triangles that where all three vertex lies in the subset. And in the third paper, we use cubical complexes, and we have an analogous subcube density. So I think when Rachel gave a talk that semester at IAS, she focused more on these density bounds. So today I won't have time to go into these. Hopefully you learn something different from that talk. And I want to just say a few words that this triangle density, it gets worse and worse as we increase the dimension of the complex. At some point, this loss beats the improvement. And so that's why we only get 0.6 in that paper. Okay, any questions? So for the rest of the talk, I will talk about cubical complexes. I mean, these are amazing objects that are interesting by themselves. So I will spend maybe a couple minutes describing them. So let's first of all, what's a 1D cubical complex? It's just a KD graph. Okay. And so we have a group gamma. We use gamma instead of G because G is a graph, so group is the gamma. And a generated set A, just some set of group elements. We look at the bipartite version of the KD graph. So usually KD graph is defined on the vertex set gamma, but here we look at the bipartite version. We have two sets, two copies of gamma. And then the edges are G to GA for each generator A in capital A. So the picture looks like this. G goes to GA, GA prime, GA prime prime. It's the same thing for the other side. So this is the bipartite version of the KD graph. Okay, now let's go to 2D. So 2D, we have two different sets of generators. And then the KD graph now on 4 copies of the group. Okay. And for A1, we have horizontal edges. So horizontal edges are given by the generators A1. Vertical edges are given by A2. And very crucially, we want to have squares in the complex. So let's look at it step by step. We start with some vertex G. We can use A1 to walk to the right, and then A2 to walk up to GA1, A2. So GA1, A2. We want that there is a different path, but now instead of going right up, we go up right. So then using A2 prime, A1 prime, and reach the same vertex. And here, A2 prime, A1 prime can be different. The crucial property, yeah.
So say the hypercube would be an example of such a graph.
Yeah, okay, so exactly.
A1 and 2 come with the source.
Yes, very good. So abelian groups, this is very easy. Yeah. The closure property is that we need this. There's for any such it has A1, A2, there's a unique A2 prime, A1 prime that reaches the same vertex, same group element. So as you pointed out, abelian groups, this is quite easy. Because in a abelian group, A1, A2 commute, so that you can just pick A2 prime to be the same as A2, A1 prime to be the same as A1, and it'll work. But okay, I guess later I'll talk about why we don't like abelian groups because they don't expand basically. Yeah. Okay, now let's go to 3D. Before that, I want to mention that these are square complexes because they're all squares, and it's actually used in this recent breakthrough of LTC construction. Yes.
Does every group admit such sets, or are there groups?
Oh, we don't know.
No.
Yeah, great question. But very, very likely for us, the LPS graph works. Yes. Yeah, okay, then let me briefly describe 3D. It's basically the same thing. So we have three different sets of generators. The KD graph is 8 copies of the group. And then each direction I is G to GAI using the AI generator. It looks like this. Okay, and again, instead of squares, we want cubes now. And the property is basically the same for any A1, A2, A3, like X, Y, Z direction. There's a unique way to complete this cube. Yeah. Okay, so this is what we call the cubical property. Okay, this is let me pause a bit for a question. Okay, so in more general, we want k-dimensional cubical complexes. And these are just A1 to AK. And crucially, we want these set of generators to have size constant, because we want a constant degree graph. This is the main reason we cannot use abelian groups. Because we want that every bipartite graph here, if we zoom into any of these, we want each of these to have good expansion. Needs to be Ramanujan. So we need non-abelian groups. Okay. And turns out we can construct this basically using LPS Ramanujan graphs. And we only need properties of these groups and generators. So basically only need these like 4 square theorems, etc. We don't actually need to rederive anything too non-trivial. We can just use the fact that these graphs are Ramanujan as a black box. So it's very, I think it's we got quite lucky that we can just directly use this. Yeah, so that's what I want to say about cubical complexes. I'll just really finish it by showing you how we use these complexes to generate these bipartite graphs. And basically, this is how we do it. We put the cubes on one side and cubes on the other side. So these currently they're the same, but they can be different. And then vertices are in here. And remember, in the cubical complexes, we have different copies of the group elements. But we also have different copies of the group elements here. Now the bipartite graph is just incidence. If this vertex is in this cube, we draw an edge. Yeah, same thing for these. And that's it. That is our construction.
The red dots are the same group element.
Oh, these are different group elements but of the same cube.
So in your picture, the cube has like.
Yeah, the cube has 8 8 vertices.
There should be like 8 red dots. Yeah.
Yeah. Okay, so I drew 4 here. Yeah.
And the 4 are behind.
Yeah, so actually, when I was practicing this talk, I thought I didn't have time to explain this, but maybe I can add a slide. Yeah, so this slide is actually there's a reason why I drew only 4. Unskipped. Yeah, I have 5 minutes left, right? So I can talk about it. Yeah, so I said that there's 2 to the k copies of the group here, but actually we're not gonna pick in here in the middle. We're not gonna pick all 2 to the k copies. We're gonna pick a subset of them, and in this case, we only pick these 4. And so how do we pick these 4? If you think of this as a k-dimensional hypercube, and we pick a code in this space, so the code C. Here we choose C to be, or in our paper we choose C to be a Hadamard code, so that every pair has equal distance, and actually every pair has k/2 distance. The reason is symmetry. We need that every pair of parts to look roughly the same. This is one key problem in our second paper when we use simplicial complexes. Each part, when we go to higher and higher dimensions, each parts look very different. For example, the first and second part looks very different than the first and fifth part, for example. But now, once we take this code, every pair of parts look the same. This is a key symmetry that we need to get our process expanded. Yeah, so yeah, thankfully I had some time to show this slide. So yeah, that's why I only drew 4 instead of 8. Okay, so let me conclude. So basically what happened was we used a random small gadget. We take this high dimensional amplifier, and then we take the tripartite length product. And this gives us lossless expanders. Yeah, and thank you very much.
Can you explain like where you find this cubical property show up?
Oh, where in the construction?
Yeah, like I mean, your analysis. Why do we need this cubical property?
Oh, because we want cubes to. You mean this?
Yeah, yeah. Like, why? Where does this show up in your analysis?
Oh, I guess because we want there to be cubes, right? Like here we're putting we're putting cubes on one side, both sides of the tripartite graph.
Yeah.
So we want these cubes to exist in the complex.
Yeah, but why do you want this?
Yeah, so I guess why you have this kd to the 1/2 when you do the 1/2 multiplicity, like that is the property you're shooting for with this construction.
Oh yeah. So even this is a high dimensional structure. So every pair of vertices either have no cubes, they're not containing any cube, or they're containing many different cubes. And so actually, so you can see for this, remember we took a Hadamard code. So this vertex and this vertex will have like k/2 generators. So there's actually you can complete this cube with k/2 choices of generators. And capital D will be like the size of the generator to the power k. So that gives k/2, which is d squared. Root d. Yeah.
And that relies on the uniqueness of the.
Oh yeah. I think so. Yeah. So you want that we want to be able to count like for this vertex, and if I give you these 2 vertices, how many cubes are there that complete that contain these 2?
And it's also why you need symmetry, I guess. If pairs were different, then this would be like a different argument for it.
Exactly. The bounds will be different for different pairs. Yes.
What is the group to choose for cubical?
So this is the LPS group graph. So it's PSL FQ. And these and the generators are according to these quaternions. So
wow.
Yeah. So that's very elegant.
4 dimensions. PSL FQ.
Two and
two. Okay, I see.
two.
Wow.
Yeah.
It's a magical.
It is magical, yes. Yeah, and ChatGPT taught us a lot about this. Yeah, Pedro?
Yeah, so the spreadness property you talked about,
Yes.
do you know if it propagates to the overall, final product graph, or is it just in, I assume you don't need to analyze that, but do you know if the property also applies to the final product graph or just to the gadgets?
Great question. You're saying whether this can. I don't know.
As in, could you
As
use
in-
this graph as a gadget?
It's gadget.
And
That's
get
why I wanted to know that.
So this premise probably is it's more like you first need to define fixed subsets on the right and fixed subsets on the vertex set, and then say that your graph has this property. So I'm not sure. I think if you run, yeah. If you don't use randomness, then I'm sure you can construct some bad sets here. Yeah.
I think there's a nice meta question there, which is you can think of all of this as trying to capture some properties of random graphs. Ramanujan-ness is like some basic thing, and you're capturing something stronger about random graphs. And the spreadness is like something yet another property of random graphs. So maybe like the question more generally is, does your construction have some other natural pseudo-random properties that random graphs have that, for example, Ramanujan graphs do not have?
Yeah, so that is a very, very great question to just study other pseudo-random properties. But specifically for this spreadness, it's actually that if you fix some subsets in any set on the other side, we'll have neighbors, right? But the neighbors are roughly spread out. So you can adversarial construct these subsets on the right and just catch these neighbors. So the quantifier is flipped. You first decide these sets, and then you pick a random.
So then it's a bit confusing. In the gadget, is every copy of the gadget independent in your thing? Like, it's not like you're choosing one gadget.
Oh, you're choosing one gadget and then tiling it. That is important. Yes.
Oh, okay. But you're still like studying just the property of this D local graph. So you okay. I was worried for a bit that you need union bound on like some.
No, union bound. Yeah. Yeah.
Cool. Are there more questions for Tim? Let's thank him again for.
Yeah. Thank you.
For those of you who are interested in this line of work, Tim also has like a collection of blog posts which explain